Okay, all right, troops. I hope. Good. I'm just checking to see. I put the microphone close to my mouth to see if the meter in this record window reacted because I forgot to check what was actually being used as a microphone. So I wanted to go over this slap together report outline with you. Sorry it's taken so long. So, anyways, we'll say something like a measurement of the acceleration of gravity. This is older papers usually it's interesting the way they use their language, and this is perfectly fine, I think, even today. So I wrote up this kind of intro. I try, and one of the reasons it's sloppy is I'm trying to write like ideas instead of just complete sentences, because I'd rather like to see you try to interpret it a little bit than to just simply copy it down. But we'll work on that one. So this is sort of like a typical intro. It's well known that objects in free fall, I guess you could say, are dropped objects, because I suppose we should think of objects that are released from rest, and they speed up. So this is at a point before Newton. If we remember, we're imagining we're back in Galileo's time. So we haven't even made the connection that when we shoot a cannonball or shoot um, any kind of projectile like an arrow, that we can describe the horizontal and vertical motion separately. So we're just going to focus right in on somebody did an experiment, and then we noticed the results, and then we're going to uh, say, wow, this, because of this experiment, that means that we can do this or can do that. And this is exactly what happens in the real world. So we could say it's well known that any dropped object does not maintain a constant speed. And so that means that, for example, the higher we drop the height, the greater the height we drop it from, the more violently it hits the ground. This is what people say in the 1800s would say. Anyway, so then we go on and we say, recently it was reported that the rate of acceleration seems to be equal for all objects. And then that's where we had the whimsical quote, Galileo. I originally put et al., Galileo et al., but I don't remember if he had collaborators. I doubt it. I think he just reported it on his own. And another way you could say it is that not so much the rate of acceleration, you might say that any object, any pairs of objects, if you like, drop from exactly the same height, will hit the ground with the same amount of velocity, or same amount of violence, or something like that. I think same amount of speed or something. Yeah. But also noted was that the author reported that it was necessary to minimize outside effects, principally the effects of air friction. One can simply imagine, and you could say something like, if I took a wooden ball and a feather that were the same mass, same weight, I dropped them, and they obviously don't accelerate the same. So, because of the results, we decided that we could make a measurement. We could attempt a measurement of the acceleration of gravity using only a single object, as this was the mechanisms available to us. Okay, so this is where you say, all right, we will determine the define velocity, and what is this? Velocity is meters per second, right? And then, or let's think about what I had in mind when I wrote this. Give me a minute. Meters per second. We define acceleration as the change in velocity or speed, as it were. And then, so we will assume that we'll assume that the force of gravity is a constant. Um, um, for the purpose of this background, we'll assume that the acceleration of gravity, um, but this may turn out not to be the case. So if we were to use our two definitions from earlier, we can create a table where an object travels at constant speed, so that's acceleration equal to 0. You have to fill in a few numbers here. It doesn't have to be perfect. And then you have these representative graphs that shows a equals 0, so it's just a flat line at 0. Right, and then I didn't do the rest. I'll leave that up to you. And then if we assume that the acceleration of gravity is greater than 0, let's say it's a constant, and so we can create this table of numbers just using the equations from above. Think about x equals 1/2 at squared, that kind of thing. And then plot these graphs. So the implication here is that we can determine an acceleration by doing a something, right? What did we do? We produced a certain graph, and we did something to it with that graph to extract the acceleration. And also remember, at the same time, we're checking to see if the acceleration of gravity is indeed constant, and that there's something about the graph we used to determine A, where we'll see what we can determine whether it's indeed a constant. In fact, if it's not a constant, we'll see that we can't do the straight line fit because it might not be a straight line. Think about it. I don't want to tell you everything. All right, so procedure. I made bullet points here. It's basically we're going to create. So this is where you don't really need to describe the air track in great detail. You just need to say that we created this ramp that kept the object suspended on a cushion of air, so that so as to minimize friction between the object and the ramp. And then let's see, do we get into and you can mention that the object was designed to minimize the cross-sectional area perpendicular to the direction of motion. And those are fancy words. It's the difference between holding your hand outside of a moving car, and when you hold your hand out like this, that's a minimum cross-section and perpendicular to direction. And this is sort of the maximum, right? And you remember what happens here. And of course you could do this with the air. Right? Maybe you haven't, but I have. And then if we assume that gravity points down at all times, and then you make this diagram where we use the angle, and you show how the acceleration of gravity is going to be equal to the acceleration. We're going to measure the acceleration of the ramp, and then we can translate that into acceleration of gravity. And let's see. Well, I made this as a question. Hopefully you quickly come off the top of your head that acceleration of gravity is greater, or meaning the acceleration of the ramp is less than the acceleration of gravity. And that's also another benefit to this this apparatus, because it makes it easier to measure the time. Because oh, I see. Now describe air. Okay, there's no particular order. Here's where you could right, now you could get into, it says here, use the fancy tilted diagram, right? So this is a cartoon tilted diagram, just really conceptual. And then now you can say, well, here's what the air track effectively what it looks like. We have the tilted track, we have the measured height, we have the measured length, we have timers set at, here you go, known positions, carefully measured known positions. And then we launched the sled, and then we recorded the time at each location, and then you go into all that we did. You know we made this. Is it the fit line here yet? Yeah. So don't forget, you have to explain why we used this V average. That was to be able to get the time in the middle of an interval, and then we to get the actual velocity, we used the equation for the average velocity. But what we ended up doing is that we used the time of the average velocity, which is the time at the center of the interval, which is and the average velocity is also the velocity at the center of the interval. I didn't really mention, but what we're doing is we're going to say we decided that our intervals were small enough so that the average velocity becomes the instantaneous velocity at the same time. So then let's see, we did 4 runs with the leveled one, the inclined one. Right, we want to see if there's any serious effects of air resistance, which is a kind of friction, or friction of the track. And so let's see, if we hope that both of them will be equal to 0. Acceleration left-right, acceleration right-left should be equal to 0 together. And if they're different, and non-zero, if they're both equal and non-zero, then, and give me a minute, yeah, then there's a residual tilt, at least the magnitudes, if they're equal. Of course, you know what I'm thinking? The acceleration has to, oh yeah, because in one case it'll make the sled go faster, in the other case it'll make the sled get slower and slower. But in effect, it means they're both in the same direction with respect to the track. It just so happens the way I wrote it here is when it's with respect to the sled. Now, if let's see, it's always 100 friction, never mind. So now if the two of them are non-zero and not equal to each other, that means that there's some friction being involved. And don't worry if you don't understand that one completely, but you can still report that. Normally you don't ever want to report something you don't quite understand. And again, basically the reason is that the way we've set this up is we're saying that when I went from left to right, the object speeded up, and when I went from right to left, it slowed down. So that implies a positive on one case and a negative at the other case. Of course, our data, everything was positive. But going back to this point here, is that we're saying with respect to the sled itself. And if the two of them are not equal, it's because F friction always points in the opposite direction of the velocity. So in the case of going down the ramp, the acceleration would point one way and the friction would point the other way. So that would mean that the acceleration in the, give me a minute, yeah. The acceleration in the direction of the sled would be less than the acceleration of the direction of the sled in the right-left in this case, because what would be happening is that if in the right-left direction, the object was being slowed down and the friction also slows it down. That's a better way to explain it without worrying about the minuses and plus. So again, let's say it again. If the object is being accelerated, the friction is going to work against that. So when the object's in a place where it's speeding up, and the friction will keep it from speeding up quite so much. Whereas if I'm in a situation where the object is being slowed down, the friction is also trying to slow it down. So then we're going to notice that the acceleration when it's being slowed down is a little bit larger if there's friction. So with friction, if the acceleration that would speed it up is a little bit less, and the acceleration that would slow it down is a little bit more. And then that's why the difference between them is going to be, well, it's actually going to be twice the frictional factor. The most important thing for us is that the friction is much less than what we notice later on. And it's much less than the friction we think we see with the track and level is much less than what we see when it's tilted. And I also just realized why that's true. Because think about it, when a track is tilted, the sled's going to go much faster. So that tells us, because, wow, you know what that tells us, guys, is I would think that it means that the air friction was the dominant friction and not the friction of the track. Interesting. Because air friction goes as speed squared, whereas contact friction is constant. So the fact that the friction we got, at least maybe you didn't, to be fair, in my case, the data somebody gave me, the friction number for the tilted was much higher, but of course that person also, their data was a little suspicious. Okay, so then let's see there, we have a sample table. We explain all of the entries, then we say we did all that. Let's see, all the rest of the data tables should go after the last page. And then the results would be the graphs, the fit parameter tables, and then the analysis is that summary table that you see in the middle where I combine all the data, and then our discussion of the actual numbers we got for acceleration and for the friction terms. And this is the result. Just mentioned that oh yeah, why is it that we don't see a negative slope in the other direction? And it's just simply because of the timer. Yeah, I have an analysis. One of the videos talks about the analysis. And yeah, and don't forget to get the acceleration of gravity. You have to divide by, I think, divide by the sine of h over, well, theta. Sine of theta, the easy thing is that sine of theta actually equals h over L, so you actually don't need h. I mean, you don't need theta. What else? Oh, yeah, and we used the standard deviation of the residuals to get an idea of what our plus minuses were. Yeah, here, A residual. So go ahead again and look at that video, and you'll get that. And don't stress about doing some kind of perfect job. Your goal is to try to use minimalist language. You don't need to go into great detail of anything, because in a paper you're just reporting results. So in this case, you basically just have to say that we decided to do this measurement because of Galileo's results. We decided we could use the measurement of only one item. I mean, ideally what we would have done is measure a lot of items. And also because Galileo mentions friction, that we tried to minimize it. And then we used this air cushion ramp, and then we used the sled that was thin, in the direction of travel. And then we move on to say how the data table, the fit line, and the straight line fit. Oh yeah, and don't forget to mention that the line is pretty straight, and so that means that it is linear. That means that the acceleration is constant. It looks like it is. We haven't proved it, right? But and then you want to really try to get everything into 4 pages, at most 6. But you can put all the data tables at the end, and those don't count for the page numbers. So You know, don't write something and then add all the data tables and go, "Oof, I made it." No, no, you don't count those data tables at the end. You only count the one example data table, the two. If there's four fit parameter tables, and then the graphs and the summary table, those all go in the main body of the report. All right. Good luck, and again, let's just think of this more as a trial run. Remember, the rubric is weighted, so yeah, the lowest possible score you could get on this is an 80%, and you'd have to really work at it, right? You know, and I'm gonna be real gentle with the grading. I mostly want to just give you feedback so you can do a better job next time. All right, see you soon.